Okay, so let's get started. So welcome to the NCTS Algebra Geometry Seminar. Today we are very happy to have Guanwen Chen from Columbia University. And he will talk about so whole structure of global smoothing of normal crossing varieties. I believe it's related also to the Sito.
Yeah, also related to Sito's talk.
Okay, please.
Okay, we can start. So first, the classical DD-bar lemma says that if X is a compact Kähler manifold, and alpha is a smooth differential form on X, and assume that partial d alpha equals d bar alpha equals 0, then alpha is d exact for some eta, if and only if alpha is d bar exact. And the D-bar lemma is very crucial in the construction of Hodge composition on the compact Kähler manifold. And in fact, okay, maybe let me give a definition here first. So for compact complex manifold and such that this statement holds, we call it the D-bar manifold. That is a not necessarily compact Kähler, but this statement holds, then we call it the D-bar manifold. Okay, and the theorem of Deligne actually says that D-bar manifold is equivalent to having Hodge composition. So the following are equivalent. The first one is that X is a D-bar manifold. And the second one is that the cohomology of X has Hodge composition. Hodge composition and for this, Hodge component is defined by the intersection of Hodge filtration with its complex conjugate. The intersection, yeah. Intersect with F bar of D minus P of X. And the third one is one of the most useful one, which allow us to consider this D-bar manifold in the algebraic setup. So if we consider two conditions, then the combined two conditions is equivalent to a D-bar manifold. So the first one is that the Hodge to the round spectral sequence degenerate at E1. So the Hodge to the round spectral sequence by definition is a spectral sequence with E1 PQ equals HQ of X omega P. And it converges to HP plus Q of C, XC. You mean that X is always a compact complex manifold? Okay, so yeah. Okay. The second condition is that the Hodge filtration is D opposed to its complex conjugate. So for all D, okay, okay. And I will explain what this D opposed means. So this means that for all P, the direction HD of X can be written as the direction of FP HD of X, and the complex conjugate of D minus in degree D minus P plus 1 of HD of X. So the D is like a summing D, P and D minus P plus 1 and minus 1. So this is called the D opposedness. So this two condition, combine the two conditions, it is equivalent to having a Hodge decomposition and also equivalent to having a D-bar manifold. So in some sense, the D-bar manifold is the maximal category that the Hodge theory can be extended to in the compact complex setup. Also, maybe just let me say something about this. That D-bar manifold actually satisfies the very strong topological constraints. It is a theorem due to Deligne, Griffith, and Morgan, Sullivan. It says that the homotopy type and actually the real as a real manifold of D-bar manifold is a formal consequence of its cohomology ring. Cohomology ring. So this means that the cohomology ring structure already determines the homotopy type of the D-bar manifold. So it is actually a very strong topological constraint. In particular, holds for compact Kähler manifold.
So for D-bar manifold, do we have Hodge symmetry? So the Hodge decomposition, does it satisfy?
Yes, because it is defined by the.
Okay, so for instance, Hopf surface is not D-bar.
Yes, Hopf surface is not the D-bar manifold.
Okay.
Yes. Real. The real cohomology. Yes. Sorry. Okay. Okay, so there's a natural question. So do we have any D-bar manifold which is not Kähler? So also to answer this question, also maybe we also want to know how does D-bar manifold behaves in algebraic operation like deformation, like bimeromorphic map, and some other operations. So operation. So first, we can know that both A condition and B condition are both open condition in the family. So actually, the D-bar lemma is an open condition if it has a smooth family of compact complex manifolds. So the D-bar lemma is an open condition. Yes. Yes. Yeah. So it means something. For example, if a 2D bar manifold has an isomorphic comoduring, then they must have the same homotopy type. But I think the ring structure, are they the same? Or, yes, yes. Yes. Okay. Maybe you can check it up later, but this is a serious stated in their paper. So, okay. Yes. Yes, right. Okay, I don't know. We can check it out later. Sorry. Yeah. Yes, I don't know. Okay. Yes, quadratic. Yes, okay, okay. We can check it out later. Oh, yes, yes. Maybe. Yes, you're right. Maybe it's weaker than the. Yeah, yeah. Okay, thank you very much. Yes. Yeah. Okay. I think you can check it out in Steenbrink's book, like in a middle chapter. There's one describing the mixed hash structure on homotopy group, and this is related to that. So, but I haven't read that chapter. Sorry. Yes, yes. I think. Okay. So because A and B are both open conditions, so having a D-bar lemma is also an open condition. In a family. And second, we want to ask how about the bimeromorphic map? And actually it's also a theorem of Deligne or Deligne, Griffiths, Morgan, Sullivan. It says that if X is a compact complex manifold, and if we have a surjective map of compact complex manifold, and such that if there exists on the surjective map such that X tilde is compact Kähler, or X tilde is D-bar manifold, and dimension of X tilde equals dimension S of the same dimension, then X is also a D-bar lemma. X also a D-bar manifold. So in particular, if X is bimeromorphic to a compact Kähler manifold, then X satisfies the D-bar lemma. So for those manifold which is bimeromorphic to compact Kähler manifold is called a manifold of Fujiki class C, so this means bimeromorphy. Then X is digit bar, or it has a Hodge composition. And conversely, there is a well-known conjecture
So we don't know whether DD bar lemma is bimeromorphic.
Yes, that is a conjecture I want to say.
okay.
And it is a, yeah, it is still unknown now. And I'm going to say something about something that is known about this conjecture. The DD bar lemma and something known is about is from Rao Shen, Rao, and Song Yang and Shang Dongyang. And there's also some other people, they point out the same thing, and maybe in the same period, like Angela, Suwa, Tardini, and Tomasini, and also Stelvig. They find that if X is a digit bar manifold, and if we consider a submanifold, which is also a digit bar manifold, then the blow up of the X along D is also a digit bar manifold. So the point is that we don't know if any submanifold of digit bar manifold is also a digit bar manifold. So that is a main difficulty in this conjecture. So the known cases is that the conjecture is equivalent to that every complex submanifold of a digit bar manifold is a digit bar manifold. Conversely, you mean this conjecture or the theorem? But here we only have this one. But I think for here it is if and only if. Yes. So yeah, so maybe it's only also if and only if. Yes. So okay. But at least this part is true. But I think the main point is the main difficulty in this theorem is to show the degeneration of Cauchy-Lorentz statistical sequence, and the opposing condition is simpler than the degeneration. So yeah, in this theorem. Okay. Yeah.
So suppose that we have a DD bar manifold without non-trivial subvariety. So yeah, I'm just wondering whether a conjecture holds for this birational bimeromorphic type.
But if you have bimeromorphy,
because you can only draw points and yeah.
Yes, if you only block points, then this conjecture holds for those bimorphic maps because points always have Dirac lemma. Yes. So yeah. So in particular for the point that Xianglin says that the conjecture holds for dimension less or equal to 3, because for dimension less or equal to 3, you can only blow up curves and points, and curves and points always have Dirac lemma. Yeah. And third, if X is a complex analytic space, and with at Walls isolated singularity, this is also a corollary of this theorem. Then actually one resolution of singularity has Dirac lemma if only if all resolution of singularity is Dirac lemma, because you need to blow out the points first, and then it is relative projective. So yeah. Yeah, so this is all I know about the Dirac lemma under bimorphic map so far. So yes. So but at least we know that if it is of Fujiki class C, then it has Dirac lemma. So the next question is, then do we have any Dirac manifold which is not of Fujiki class C? So the answer is yes. There's several examples, and the first one is due to Campana, and also by LeBron Quinn. Because we know that Dirac lemma is an open condition in deformation, but actually the Fujiki class C isn't. So we can deform some Fujiki class C manifold to get some manifold which is now Fujiki class C but satisfy the Dirac lemma. So this is what they consider. They consider some Moshadon twistor space and deform it. So and then get some Dirac manifold which is not of Fujiki class C. Deforming some. And second, there are also some examples by Angela and Kasuya obtained by in some soft manifold. So for soft manifold, it means it is isomorphic to G quotient H, where G is a solvable Lie group, maybe connected. And H is a closed-up group. And yes, by consider this kind of soft manifold, they obtain some example. But some example are in Fujiki class C, but some are not. And the third, this is a main topic today, is a Friedman and Clemens construction. So what this construction means is obtained by deforming the Calabi-Yau threefold with only ordinary double point. Yes, so we assume that X is projective. Calabi-Yau threefold. And C1 to CR are disjoint rational curve on X. And we assume that the class of C1 to CR generates the H4 of X. And also, there is a what we call the Friedmann relations. And this is a relation in H4 of X. It has a non-trivial relation whose coefficients are all non-zero. Then Friedmann and Clemens show that in this construction, if we contract those rational curves to an ordinary double point, and it is a locally analytic construction. So yeah, so this is obtained by yeah. Sorry, I forgot to write on that. Yeah. Yes, because then the local neighborhood can be contracted to ordinary double points. Yeah. Then they show that then in this under this condition, X bar is smoothable. Then X bar is smoothable. And it can be smoothed. For smoothable, I mean there is a family from X to these, and the central fiber is this manifold, and the general fiber is like XT. And in this case, XT is a Calabi-Yau threefold. OXT. And also because you have already contracted all the rational curves that spend H4, we can show that in this case, H2 of XT is 0. So in particular, it is not Kähler because H2 is 0. So in particular, not Kähler. And in fact, it is not of Fujiki class C. Yes. And there are actually many examples of this type which produce a lot of non-Kähler Calabi-Yau threefolds. Yes. In the assumption, or you mean this one? This. I mean, I think solvable. it's just because the Hodge composition or that those things can be computed in this case. So yeah, you can consider other kinds of manifold, but maybe it's not easy to compute the Hodge composition. I think it can be characterized in this way as for soft manifolds. You mean not the soft manifold or something, or what's your question? Oh, not of Fujiki Kasi. You mean, are there any example of that actually is not close? I don't know, sorry. Yeah. Yeah. Yes. Right. Yes, you're right. Okay. Okay. So maybe let's continue. So then the theorem by Friedman in 17 and Qu Li in 22, they also show that, in fact, this general XC is a D-bar manifold. And H3 of XC is polarized by Caprada. Yes. So this is the motivation of our work, our MEM theorem today, that because he shows that some global smoothing has the lemma, and also the Hodge index can be computed. So the question we are asking today is about the general phenomena behind the theorem here. If in general, we have a singular compact complex manifold and consider the global smoothing, when do we have this similar kind of properties? Okay. Yes. So if we are given, say X, a singular compact and a complex space, and we assume it has a Kähler resolution of singularity, and we also assume that if it is smoothable, that is there is a E equals a central fiber of a family, and then it can be smooth to some smooth general fiber. Then we want to ask the first question: when is this XC or D-bar manifold? And second, if one holds, can we compute the Hodge index? on the middle cohomology of XT by car product. Okay. But let me point out that this formulation of a clustering is in fact vague because this singular compact complex analytic space might have several different ways of smoothing. So it is actually not possible to use X to determine what the XT is and what Hodge theory on XT is. So actually, we need to take a semi-stable reduction, or maybe let me state it in the converse way. We need to assume that that this singular thing is a simple normal crossing variety and also d-semi-stable. And I will explain what d-semi-stable means and why we need this assumption. Okay. So let me first define what the d-semi-stable means. It's a definition due to Friedman in 1980s. A simple normal crossing variety is d-semi-stable if the singles T1, T1 is defined as the ext sheaf is isomorphic to the structure sheaf of singularity X. So how can we think about this singles T1? It's actually the sheaf of local first order local deformation. So if it is isolated to the structure sheaf of singularity X, it means locally at the singularity has only one way of smoothing. So this is why under this, one of the reasons why under this condition, it is possible to recover what XT is from X, because it has only one way of smoothing. So it has a control on the global smoothing. And the fact is that first, if we have a semi-stable degeneration, then the central fiber is d-semi-stable in this sense. So actually, it is the central fiber of the semi-stable degeneration. But if we state it in this way, it is not necessary that this variety is smoothable, that it comes from a family. So also a second fact due to Friedman is that the d-semi-stable variety itself carries a limiting mixed Hodge structure. Which is compatible with Steenbrink one if it has a smoothing, like it comes from a semi-stable degeneration. So it somehow shows that the limiting mixed Hodge structure in the semi-stable degeneration only depends on the central fiber, not on the general fiber. So it is why it's possible to recover the Hodge theory of the general fiber from the singular fiber, because yes, it only depends on the central fiber itself. Okay. And the third, maybe let me give an example of what this condition means. If the central fiber has no triple point So so for example, it looks like this, only, and this is called X1, X2, and this is D. Then D semi-stable for this normal crossing variety means that the normal bundle tensor are trivial. The limiting mixed-out charger is on, but it's a mixed-out complex on the single fiber, right? It is defined on the like a limiting cohomology, but yes, in CETO you have said that it can be computed by this log relative log Laurent complex and taking the tensor X0 and taking a hypercohomology. Yes, and this is a isomorphic to the limiting mixed-out charge, limiting cohomology, right? Yes, this is what the Lynch canonical extension is, but this is a shift on central fiber, and Friedman shows that this shift can actually be recovered only from deformation, only from the information on the central fiber. So it doesn't depend on this shift, only depends on, in modern language, the log structure on X. So not on the. You mean the central fiber? Yes, I will. Actually, D semi-stable is equivalent to it has a log structure. So yes. Yes. Okay. Okay. So there is also a classical question that is how to recover how to get the smoothing from a D semi-stable variety, because what we want is a semi-stable degeneration. But if you start with the D semi-stable variety, it's not necessary that it has a global smoothing. And in fact, the difficulty is that the deformation of the D semi-stable normal crossing variety is usually obstructed. So, but there is a very brilliant observation by Kawamata and Namikawa, which says that if you consider log deformation instead of the usual deformation, then it behaves better. So yeah, let me state this. It's a point by Kawamata and Namikawa. Yes. So they find that the deformation, log deformation, is behaves better. So maybe the first part that of facts they find is that if X0 is a simple normal crossing variety, then X0 has the log structure. If and only if it is D semi-stable. So if you consider the deformation with the log structure, then we can exclude a lot of locally trivial deformation which doesn't smooth. Then the deformation space becomes smaller. Then it is possible to get unobstructedness in this setup. So then there are the current work. There is actually a very deep theorem, the logarithmic Bogomolov-Tian-Todorov theorem. And it is by Kawamata and Namikawa in 1990s, but under certain cohomological condition. And some recent work by Chen Liang Ma, and also by Fulton, Philip, and Radat. that if we consider the semi-stable simple normal crossing variety, which is Calabi-Yau, such that the Calabi-Yau, and it is proper algebraic variety. So it is not only an analytic variety, but also a proper algebraic variety. Then they show that in this case, the log deformation of X0 is unobstructed. And in particular, S0 is smoothable. Or maybe semi-stably smoothable. That is, then it comes from a semi-stable degeneration of some family. Yes. So, and actually, this logarithmic Bogomolov-Khian Todorov theorem is enough for us to construct many non-Kähler examples of Calabi-Yau, non-Kähler Calabi-Yau threefold not of GK class C. So, yes. I think this is also a motivation of the question that we state here, that how can we know about the Hodge structure on the general fiber, because currently there are many such kinds of examples of non-Kähler global smoothing. Okay, yeah. So yeah, so let me give such example here. So, and yes, and first definitely we have the Friedman and Clemens contraction, that one, and except for that one, we also have the one from Kodaira for surface case. Is Kodaira construct the family of surface, actually the semi-stable degeneration, and its central fiber is like, yes, like two half surface, no, two Hirzebruch surface, and doing like this. So this is like S1, 2 copy X1, X2, and X1, X2 are both Hirzebruch surface. And it glue along some, because Hirzebruch surface is a positive section and a negative section. So we glue a positive section with negative section of X2 and glue the negative section with a positive section from X1 and X2. Then this is the normal crossing variety. And we can show that it is D-semi-stable because it satisfies this condition. And the XT, the general fiber in Kodaira's family, is a Hopf surface. So this example shows that it is not necessary that the general fiber has d-bar lemma, because that is a family such that the central fiber is like satisfies our assumption, and but the general fiber doesn't have d-bar lemma because H1 of the Hopf surface is like one dimension. Yes, so we want to compare what is a different from Kodaira example and the Friedman-Clemens example. What's the difference between the two? Yeah. In this case, yes, in this example, then H2 is 0. So the point is for H1, right? And H1 is one dimension. And we can see that the one dimension only focus on weight 0 part, not on the weight 1 part. So yes, so this is actually what we need for in our theorem, that we need the weight filtration only on the weight 1 part. In this case, if it is only in the central part, then, or maybe it is the wave field association is the monodromy wave field association that you introduce in the Shito's talk, then it has then the general fiber will have D-Dubar lemma. Like, but I will explain that in more details later. Okay. And the second one is by using this logarithmic Bogomolov-Tian-Todorov theorem, the example constructed by Hashimoto and Sano, and also some higher dimensional case by Sano, that they consider the what we call a T-ring degeneration that is given by two projective variety gluing along a subvariety. And here H1 and X2 are what they call the quasi-Fano variety. So by this, they mean that there exists a Calabi-Yau threefold, a Calabi-Yau manifold in the negative K section, anti-canonical one. So it's not necessarily Fano, but its negative K contains a smooth Calabi-Yau section. And assume that the two Calabi-Yau, the two sections are the isomorphic, then we can glue along such D. So, but because they want to construct many examples, so what they want is that D is a Calabi-Yau manifold. It has an automorphism of infinite order. So for example, if it is a Shen's Calabi-Yau manifold, then it has an automorphism of infinite order. For example. And then they glue along this automorphism of infinite order. Maybe if this automorphism is called phi, then glue along phi k here. But the point is that if you construct the normal constant variety in this way, it might not be D-semi-stable. So what they do is that they further blow up X1 and X2 to make the normal bundle trivial so that it becomes D-semi-stable. And then it becomes a D-semi-stable Calabi-Yau normal crossing variety. And then we can apply the logarithmic Bogomolov-Tian-Todorov theorem to get a global smoothing. And they use this method to show that actually there are many non-Kähler Calabi-Yau manifolds whose B2 can be arbitrarily large. In particular, it is an unbounded family. So yeah. So then the theorem by Hashimoto, Sano, and Sano, yeah, they show that in this case, for n greater or equal to 3, there exists non-Kähler, actually not of Fujiki Kasi, Calabi-Yau n-fold, maybe let's say x m, but with another parameter, let's say a, whose B2 as a goes to infinity. So the, yeah. So yes, so there are many families of this type.
Also, usually how to check that the smoothing satisfy her DD bar lemma?
Yes, that is the main point today.
Ah, okay.
Yeah, yes, this is the main question we stay there. And I'm going to answer this question now. Okay, I have 30 minutes left. Yes. Yes. So actually by our main theorem today, we can show that these examples all have Dirac lemma. So yes. So now we can come to the main question, answer the main question today. I think it's spent too much time to give a general picture of what this question is. So now the assumption is that we have a semi-stable degeneration. Because we are not going to deal with a deformation theory, so we assume that it comes from a deformation, comes from a family. And so the puncture disk here is like X star. So we assume this F is a semi-stable degeneration. Of compact complex manifold, and assume that each component of a central fiber is scalar. This is only, or more generally, that each k-fold each intersection of the central fiber support the Dirac lemma. It is a condition that we need to have the limiting mixed Hodge structure. Yes. Okay. Yeah. Then, as in the Scheider's talk in Shito, then we have Steenbrink limiting mixed Hodge structure. So the first, that for D, then the Hodge bundle, maybe a cohomology and tensor O delta star. And if we include it in the higher hyperdirect image of the reactive dualizing sheaf, then this is the Lins canonical extension. As in Scheider's talk in Shito, then yes, then the cohomology on these has a canonical extension to X on delta. And the second, under this condition, Steenbrink shows that the module is unipotent. And the third, under this condition, Steenbrink shows that in this case, there is a limiting mixed Hodge structure, like HD limiting, and also wave filtration, what I call Steenbrink wave filtration, constructed in this context, and limiting Hodge filtration, and such that the nilpotent part is a morphism of mixed Hodge structure of type -1, -1. Okay, so maybe let me state 4. Then as a corollary of this theory, you can also always have the E1 degeneration degenerate at E1. So recall that for Dirac lemma, we have two A condition, B condition. A condition is a E1 degeneration, and B condition is a D opposing condition. So in this setting, we always have the E1 degeneration. So the only non-trivial part is the oppositeness condition here. And why do we have the E1 degeneration? Is by the semi-continuity theorem part. We can compare it with a central fiber, but a central fiber is kind of have a Kähler condition that it has degeneration, and we can use the comparison to get the degeneration for general fiber. Yes, okay. And on the other hand, also in the Scheider's talk, we have Schmidt's limiting mixage structure, which is actually different from Steenbrink's one if it doesn't make any constraints. Okay. So we have Schmidt that Schmidt says that if we have the like in an abstract variation case, if we have an integral polarized variation of Hodge structure, on the puncture disk, then under the Linz canonical extension, this F can be extended to some F tilde to the central fiber, which give a polarized mixed Hodge structure. Then under the Linz canonical extension, it degenerates to some polarized mixed Hodge structure. And this is what we call the limiting mixed Hodge structure. But in this case, both integral and polarized are necessary here for him to construct the limiting mixed Hodge structure. And yes, I will explain what this mixed Hodge structure is. This I will call it H and W. And this wave filtration is called the monodromy wave filtration, and also the Hodge filtration F. So I will explain what this monodromy wave filtration is. It's actually defined also in Schito by Scheider. So what is this Wn is? So if n is a nilpotent element, a nilpotent operator on a vector space V, then there is a maybe okay. Then there is a unique monodromy wave filtration center at D of V such that if this is called W, the wave filtration is called W, then N send Wi to Wi minus 2. And also, the gradient piece is an isomorphism from GR WD plus L and center at D of V to GR D minus L B is an isomorphism. It's by Schmidt that there's a unique wave filtration of this type and constructed by using the nilpotent operator N. And in Schmidt's case, he takes this wave filtration and then show that this wave filtration forms a mixed Hodge structure. And also there's a polarization here. Okay. Yes, so So what we mean by the polarized mixed Hodge structure? So because the polarization here gives you the polarized form S, so what we mean by a polarized mixed Hodge structure here means here is that in this case, if we consider the primitive part of unprimitive part of its kind of Lefschetz decomposition, it defined as kernel of n to the L plus 1 of GRD plus LW yeah, but it must be, maybe I could write H because it must be a mixed Hodge structure in this case. GRWD minus L minus 2 of V. So we call this primitive part. Then this primitive part, Hodge structure on this is polarized by the form as n to the L. This bilinear pairing. So yeah. So n to the L sends a vector to this space, but this is isomorphism. So we show by this pairing, it is a polarized Hodge structure. Yes, sometimes they give the same. So yeah, sometimes they give different. So first, it must have polarized Hodge structure here, but in general, the cohomology is not polarized. You mean when the output are different? Yes. If you, yes, I will say that in some case, when the two inputs are the same, then the output will be the same. I will mention this. So yes, yes. So yes. Yes. They use different construction, but there's a very deep theorem actually that yes, the two-way filtration in general not the same. But we have a theorem due to Steenbrink. And actually Steenbrink's proof is wrong, but the proof is remedied by Saito, Usui, and by Guilla, Navarro, Asner, that if we assume some Kähler condition, very strong Kähler condition, if there exists a class L in H2 of the central fiber, which restricts to the Kähler class, or K4 intersection, then the two filtration are coincide. So this condition means that the Kähler class on each component of the central fiber can be glued to a global Kähler class on the singular space, global class on the singular space. In this case, that they can show that the two filtration are the same on the Steenbrink setup. Yes. But this is actually one of the very deep theorem in limiting mixed Hodge structure. You mean K4 intersections? Because the central fiber is a simple Minkowski variety, so he has a double locus, triple locus, or something. So I mean, all those intersection of the it's the Kähler class on those. Yeah. Yeah, for example, if a total space scatter or algebraic, that it comes from projective family or something. Yes, 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 yes. But usually in the, I think the non-Kähler global smoothing case, this condition doesn't hold. Actually, yeah. Okay. Yeah. So maybe I can state our main theorem today. So our theorem is that actually the converse is true in some converse of Schmidt theorem is true in some sense. If under this condition, we assume that W thin-beam wave filtration equals the monodromy wave filtration centered at D on the HD of limiting mixed structure, then the general fiber has such decomposition. So it's like of a converse because Schmidt's theorem is just saying that for the degeneration, but if under polarized case, then using the monodromy wave filtration is a mixed structure. But what we are proving is that if we use a monodromy wave filtration is a mixed structure, then we can recover the general fiber and show that the general fiber also has Hodge composition. So, you mean algebraic case or? But so yeah, so in non-algebraic case, we only have the one on the middle cohomology. So this condition doesn't need a polarization. You mean the D is any D? D is any D. So but this is in Steenbrink's setup. So it has the limiting mixed structure on any D of cohomology. So the limiting cohomology. So yeah, given any D. Yes. But in Steenbrink case, we don't need a polarization. I think this is the point. What the difference between Steenbrink's one and Schmidt's one? Yeah. And yeah, right. Okay, so this is the first theorem today. And also we want that if in this case, because as he said, in this case, in general, we don't have the polarization on the all degree of cohomology, but at least we have the polarization on the middle degree cohomology by cut product. Because yes, in this case, we don't need a cataphone or something to define the polarization. So we have the bilinear pairing on cut product. So we are asking if we can compute the Hodge index on the middle cohomology under this assumption. So yes. So now in this setup, we assume that the D is dimension, middle degree dimension, because we want to discuss the middle degree case, and this theorem holds. I mean, assumption of theorem one holds for this D, then yes, so we have the polarization actually. So let me write down what the polarization is. So from the Steenbrink setup, we have the higher direct image of relative dual lightning sheaf. And it can be tensor with RD. And now D is a middle degree, so it can be tensor with D. And it is sent to R2D by the product structure on the relative log-Duran complex. But this the higher one is isomorphic to RF star D of the relative dualizing sheaf. And the relative dualizing sheaf has a natural one comes from the duality theory, the trace map to O delta. Yes. So this is a bilinear pairing or the polarization we have in the Steenbring's case for middle cohomology. Actually, we have n Rn to Rd minus n, but in that case, yes, we don't have a natural pairing for fixing 1D. Yes. So we let this pairing to be defined as Q. And actually restrict to the central fiber is the one we say the polarization on middle cohomology. On the limiting cohomology. Yes. And we let S to be -1 to the 2 of D minus 1 Q. Yes. And we can define the index like S plus P D plus L minus P, S minus P D plus L minus P to be the index on the P D plus L minus P component. Of the premium P D plus L part. And this is defined the same way that we stated in Schmidt's argument. This is by the pairing as of this one active and maybe let me place the C. So the C is a Weil operator, which is defined as -1 square root of -1 to P minus Q in the Hodge component of P minus Q. And we multiply it by -1 to the L times here on the second component, which is parallel to the Schmidt's definition of polarized mixed Hodge structure. But why do we use -n here, but use n in Schmidt's setup? This is actually a Kreis-Sato here, Kreis-Sato things here, because Schmidt's N is actually different from Steenbring's N in a negative sign. Yes, this is a Kreis-Sato convention that even experts in mixed Hodge theory can make this mistake. So they use the same notation, but they're actually different from a negative sign. The point is that in Schmidt's case, we will take the Lins canonical extension, and we will use the inverse of monodromy to trivialize the local system. And that inverse of monodromy gives a negative sign. So Schmidt just choose that one, and Steenbring choose a usual one, like a Picard-Lefschetz monodromy, and take log T. So they will be different from the negative sign. So here we choose the negative N here, so that we are in the Steenbring setup by using the Schmidt's terminology. Okay, and yes, okay, so we have this Hodge index. Under the condition, we can define this index, and then for L, because of Lefschetz decomposition, we have the Lefschetz decomposition defined by D plus L. Yes, there's a Lafayette decomposition by the definition of the unpolarization, monodromy mean weight filtration there. So by using this Lafayette decomposition, we can take a sum of all positive and negative Hodge index and paralleling to this, according to this Lafayette decomposition. So in this case, we define the sum. Okay. Yes, so we define the bigger as plus L or minus P, D plus L minus P to be sum over R greater or equal to max, negative L0 of S plus or minus P plus R, D plus L minus P plus R. So this is according to the Lafayette decomposition, and we take a sum corresponding to one Hodge component. And then by using this, we can state our theorem now. It says that the signature we put the V operator here on the general fiber. Maybe okay, maybe on HPD minus P, the PD minus P part of the general fiber, because now we know that it has a Hodge composition by theorem 1. So then it is sum of this bigger S from 0 to D, and then sum from this bigger S of minus part to from 0 to D. So it shows that the Hodge index of the general fiber, middle module of general fiber are all determined by the central fiber sum index calculation of a limiting mixed Hodge structure. And those computation can be computed only in terms of the information from the central fiber. So yeah, but I think I don't have time to show you how to compute those things. So maybe let me give a remark here. The N-square case in theorem 1 and N-square equals 0, D equals 3 case. Theorem 2 is also proved by Zhongru Li and also by Tarasano independently. But actually, the assumption is not needed. So yeah, So maybe in the last few minutes, let me sketch how to prove the two theorems. Yeah, so there are actually two new ingredients. So the first ingredient is that maybe is comparison with a Nilpotent orbit. So for simplicity, that we focus on the polarized case. Here, because in this case, we have the Fourier domain or the classifying space of Hodge structure. Of the fixed dimensional in each Hodge component, and we let D check to be a compact dual of D. So this D check is actually a smooth projective variety. And the D containing D check is a real open subset. So what's the picture we have here is that we have a larger D check, which is a compact dual, and we have the real open subset, which is D. And what we have now is that we have a curve, and we don't know if it comes from outside or comes from inside, but it degenerates to the boundary here on the boundary of D. And we want to show that it actually comes in D, but not the outside. But if it is an arbitrary curve, then definitely you can go outside or inside. So then the theorem should not be true here. So the point is that we ignore the monodromy here in this picture. So the monodromy actually prevents it from going outside and actually let it go inside here. So what is a monodromy here actually? How did the monodromy prevent it from going outside? So in the polarized case, actually we have the theorem due to Catani-Kaplan-Schmidt. It says that if we have a polarized Hodge structure, then exponential DNF is a nilpotent orbit. So the nilpotent orbit means that exponential DNF lies in D, lies in the interior of a classifying space of Hodge structure for imaginary part of D is large. So it somehow shows that although we don't know what the original curve is, but there is somehow a nilpotent orbit which must be serve as the leading term of the original Hodge filtration, but it lies in D. And this is our original Hodge filtration F. Yes, and the nilpotent orbit and the original Hodge filtration are very close because of the links in canonical extension. So they can only be different by some terms of exponential decay. But yes, but this is not enough because even if they will converge finally, but it is possible that it goes from here, converge, and it goes from the curve goes from here and converge, and they are one is inside and one is outside. So another thing is that we need to show that exponential DNF lies enough inside the Fourier domain so that if F is approximate this exponential DNF enoughly close, then F is still lies in the interior of the Fourier domain. So yeah, so actually, if we use this picture, then using Schmidt theory, actually we can give a proof using Schmidt theory how this exponential DNF lies in enoughly interior in the Fourier domain. So this is because that this one is horizontal. And then it implies that it is bounding Poincare metric. And then Schmidt uses kind of technique to prove the Higgs nilpotent orbit theorem. So now in the polarized case, we can exchange the rho of the exponential DNF and F so that the converse of the theorem holds. But we know that if we use the Schmidt theory, we can only deal with the polarized case because a lot of Schmidt's estimate need to assume it has a metric, it has a polarization, and use a Lie theory. So the second thing is that if we want to go beyond the polarized case, then we need to avoid using Lie theory. Yes, and this can be done by generalizing the estimates in Friedman and Chili's argument, which is more elementary and only depending on linear algebra, because somehow we only need to estimate this kind of exponential DNF, and it is just a linear algebra thing. And we can estimate this exponential DNF directly using linear algebra and show that it has something good estimates. For example, we can compute the asymptotic order of each eigenvalue of exponential DNF and compare it directly with the eigenvalue of F and show that yes, the two eigenvalues actually are actually quite close, so that the Hodge index must be the same as exponential DNF in this case. So yeah. So then by using the generalizing those techniques, then we can obtain the second theorem. Okay, maybe I can stop here.
Thank you very much for the interesting talk. Are there any questions?
Yes. Yes, yes.
So in your theorem, you're saying that if the filtration inside, then the smoothing is supposed to be position.
Yes.
So it doesn't.
Yeah.
Therefore,
yeah, for Caldera example, because the H1 case, if the two filtration coincides, then the one dimension should focus on W1 over W0, way1 part. But if we compute it directly, then it lies in the way 0 part. So the two filtration are not the same in that case. So maybe I can write something. Yes. Okay. Okay. Let me show you. Okay. Okay. Yes, it is here. Yeah. Yes. Okay. Use this one. Yeah. So in that case, we have two Hisabu surface. So let me use the notation. This is called the S1. And maybe this Hisabu surface called S2. And this one is D1 and D2. Yes. In this case, we can calculate the GR0 of a Steinbring wave filtration on H1 limiting. And by definition, if we use, by definition, it is a wave spectral sequence of 1,0 part of E2. So by definition of a spectral sequence, it is co-kernel of H0 of S1, the rest on H0 of S2, and then take a restriction map, alternating sum of a restriction map to H0 of D1, the rest on H0 of E2. But because of sign, up to some sign, actually because this is the first intersection, I think the sign is all positive. In this case, we can show that this is isomorphic to Q, I think. Yes, because it's 1, 1 and -1, -1. Yes. So in this case, it lies in the zero part. So not a. Yes, right. Yes. Yes. Right.
So in the statement about the existence of a limiting Hall structure, so we have this Kähler assumption.
Yes.
So is it possible to, yeah, so if we don't want Kähler, but just only DD bar, are there some replacing condition to guarantee the?
You mean on the middle
middle
cohomology?
cohom-
Yeah, yes, but we can assume that each k-fold intersection of a central fiber has DD bar lemma. This is what the situation that the Sembring theory can be applied. Because we only need like
I see.
the residue map to reduce to the Hodge area of the each component k-fold intersection, so that we have a degeneracy and some Hodge structure on each k-fold intersection to construct the limiting mixed Hodge structure. Yeah.
So we don't need to have a global class.
Yes. So we don't need that Sembring cycle as use case. But this is a very strong condition, much stronger than the existence of limiting mixed Hodge structure. Yes. And usually in all of the non-Kähler examples so far, like that I list here, like a Kodaira case of, or the Kleiman-Friedman case, or the Sano Hashimoto case, this condition doesn't hold. So, yeah. So in these case, if the condition doesn't hold, we need to calculate the limiting mean structure directly and see what happens and apply the theorem. Yeah. Okay.
Okay, so I have a strange question. So, yeah, in your opinion, what are the examples of, yeah, so complex manifold satisfying DD bar lemma, which is the least non-Kähler. I mean, how to say?
The least
far from Kähler.
Far from Kähler? You mean not of Fujii class C or?
Yeah, or
the least one, or?
I don't know how to ask this question, but yeah.
Yes, I think maybe not of Fujii class C is one notion that we have so far that is far from Kähler, or yes.
Okay. Oh yes.
Yes.
So DD bar lemma seems to be very analytical differential geometry.
Yes.
Why you cannot do any analysis of differential geometry kind of stuff?
I think the problem is like the Linz formulation, like it reformatted into the degeneracy of E1 Hodge-Suzerain special sequence and also de-opposedness. But the de-opposedness condition is kind of somehow analytic, but in algebraic geometry, we can replace it by something like homomorphy or something to study it. Or
so for example, we try to use analysis.
Yes.
Because the problem is global.
Yes.
So local we could do some kind of Poincaré.
Yes.
So sometimes we should need some kind of analytic study of the I would say the norm of the analytic property.
Yes.
So that's the problem we are going to encounter.
Yes, but maybe it's possible, but then because singular fiber is like a simple normal crossing, we need some kind of PDE things for simple normal crossing.
So what's that kind of PDE problem?
I don't know actually. Yes. Yeah.
Are there further questions? If there's no more question, then thanks Guangwen again. So thank you very much.
Okay, thank you for attention.